Yeah, so to welcome all to another session on from SD Skills on the book CTCI, the book club CTCI. So today we'll be discussing the chapter 6, which is about math and logic puzzles. And in this chapter, I'm not going to go more in details about the puzzles, but I will just discuss more about the maths and logic, whatever is associated with that, right? Okay, because I think puzzles are not being asked nowadays, the brain teasers and all that. So we just stick to the math or the logical side. And in few cases, we might go just to discuss some of the very popular ones. Okay. So to start with, I hope you are able to see my screen, right? The note, one
Yeah,
note. Okay.
yeah.
Well, so the first, we'll try to go through some of the theory, what is already there in this chapter. And so he talks about the book talks about some of the common approaches as well as some of the essential knowledge which is required for tackling all the mathematical problems and all that. But I don't see much of the mathematical information, but there are a few of them. So let's discuss whatever is there, right? Okay. So the first one is about prime numbers, right? So he says that any positive integer can be decomposed into a product of primes, right? And this is what is the example here, 84, right? So 84 is actually 4 into 3 into 7, right? So if we see, it is actually, it can be decomposed into uh, product of all the primes, right? 2, 3, and 7. So they have also marked the others which are raised to 0 because they are not counted, right? So just to show that every prime, any positive integer actually can be represented this way, right? So now, to take some examples like on the divisibility and all that stuff. So he says that if you have uh, an value of x, maybe something like any variable x, and it has something like 2 raised to j 0, okay, multiplied by 3 raised to j1, okay, and 5 raised to 5 raised to j2, so on and so forth. And if you have another variable like y2, which is equal to 2 raised to uh, k0, okay, and then 3 raised to k1, okay, and then 5 raised to k2, okay, so on and so forth, right? So there will be a number of things after that, right? So in this case, now, if we want to find how we can actually deduce a GCD, right? So like if you want to find GCD between these two variables, so what we can do is we can go to each and every variable here for every term, the decomposed term, and then take the minimum of these value, the power value, right? So if the GCD can be variable expressed in this terms of, like, if we are doing the GCD for these two x and y, okay, x and y. So what he says is you can actually express it like this: 2 raised to, okay, minimum of uh, j0 and k0, okay, and it is for all of them, right? So for other factor also, and the same thing can be done for LCM also, right? So if you have to find an LCM of these two, so you can actually say 2 raised to, in this case we have to say the max, okay, so the max of j0 and max of k0, and so on and so forth for other uh, product prime products like maybe 3, 5, and whatever it is, right? So we can easily express these GCD and LCM, and then he has given some examples in that and said, like, if we multiply GCD by LCM, the same thing, just to get some of the tricks, and then say it will actually evaluate to x multiplied by y.
Product of two numbers. Yeah.
Yeah, the product of two, right? So these were
Does
some
it
of the, yeah.
does it show how to decompose a number to to a product of primes number.
Right.
Divide 2, right? I mean, 2,
So
3, and
yeah, so like 5 to the 0 is 1, right? 11 to the 0 is also 1.
Mhm.
Are those right?
Yeah,
Does it?
that's
I
right.
mean, does the book show how to decompose a number to the product of prime number?
Well, that is what it is, right? So if we say 4, 2 raised to 2 is 4, 4 into 3 is 12, right? And 12 into 1 is still 12, but 12 into 7 is 84. So he's trying to see, we can easily decompose any of positive integer in a product of primes. So he's just showing this. So in case if you need all these things, so it is more handy to you, right?
Yeah, but how he know? I mean, decompose, right? So he know he have to know. They have to have number 2, have number 3.
I think like this 84 is there. You divide it by 2, you'll get 40. Sorry, 2 4 are 2, right? And now you'll divide by 2, you'll have 21. Now 3, you will have 7, right? So here you can know that there are two 2s and one 3 and one 7.
Yeah, so you're saying that if you want to find out
Prime.
what are the primes
Yeah,
actually involved
yeah.
in that. Yeah, that
But
is true. So there are different ways also of getting primes.
but the way Sasha did it does not show, like, for example, 5 to the 0 or 11 to the 0,
Yeah,
because
Yeah,
that
yeah, that's not there. But if you see the prime 2, right? Prime 2, 3, and 7, they are there, right?
yeah.
So if the prime is not there, it means it is raised to 0,
yeah.
right? So it's just showing. So you don't have to have all the primes in each and every number, right? So if just to show in a very general way, to make it more generic. So if that prime number is not there, he's just raising that to 0, just for our understanding and to show that how it can be decomposed,
Okay.
right?
But raise to 0 is okay, it's 1 and then
Is always
multiply
one,
it 1.
right?
Okay, got it.
Yeah,
Yeah.
yeah.
Mm.
Okay, yeah, thank you. So then what is talking about, what they're talking about in the book is like if you want to check uh, how whether a number is a prime or not, right? So for that, I'll just go to my, okay, let me go to my playboard. Okay, I came back here. Sorry for that. Okay, so this is about the man. Okay, so let me share my, okay, the screen. Okay, so now he has actually shown a couple of functions of how to check how to get to a prime number. And he also the book also says that it's very common, uh, these questions are usually asked, right, most of the time. And if we are supposed to find out, if we are given a number, then how do we find a prime number? So they are very easy, it's not a big of a deal, but just wanted to represent and walk through them again. So if we are given a number n, and if you want to find its prime, the most near way would be actually just look, if the first is if it's less than 1 and 2, return false, or then you go and start dividing that number by 2 as a function, right, from 2 to n. So each number you go, okay, and then whenever you see any of the number is not divisible, right, then you return false, right? So at the end, when you come here, so it means that it's not divisible by any number, and therefore it's a prime number. Okay, so this is one of the quickest way and a very brute force way of doing that. So there are other ways also of doing it, and you can make a slight improvement on that, in the sense like, we can do the same thing, right? But in this case, what it does, you don't have to actually go all the way from 2 to n, right? So it can be a square root of n also. Okay, so this is one way of doing a square root for n. And why for square root for n? It says like, if we have a number, right? If we have something like a 36, right? And then if you want to find if it's a prime number, I know this is not a prime number though, right? So, but you'll start with 2. So if you start with 2, 2 multiplied by 18, 2 multiplied by 18 is 36, right? So if you start with 2, So its complement is almost 8, right? 18, sorry. So this, if you are able to successfully divide this by 2, then you don't need to go and test for 18, right? So that
Yeah.
is the reason you actually go only to the till the root of n. In this case, it is like 6, right? So if you check all the prime numbers from 2 to 6, that's enough, because they are the same even if you go ahead and keep on dividing. But in this case, you save a lot of time complexity, and there is some optimization. So this is one of the things what was discussed in the book.
It's more efficient also
Yeah,
because
it's more, yes, more efficient that way, because we just going to avoid so much of
iterations.
yeah, and also processing and all the stuff, right? Okay, so now he talks about one of that, the sieve of Erythrosines, right? Erythrosthenes. Okay,
Yeah.
so that's the very famous one, and I think most of we actually have gone through it at some point of a time, and just thought of also going through the way it's implemented in the book. And I think it's most of the way it's standard, right? So what it says is, if you are given a number, like this is the number, max number, right? So what you need to do, you need to form a table, okay, of all Boolean values of this number plus one. Okay, so this is just a flags table, and I'm setting all of these flags to true. Okay, but the initial flag 0 and 1, which represent number 0 and 1, they are not supposed to be in the prime, right? So we just set them to false. Okay, and then a prime starts from 2. And the same way we do again when we go through the while loop, and for the square root part of max, right? We just look for that many prime numbers, go through this table each and every time for every prime number what we have selected, because this is prime we'll select for now. Then we'll cross off all the flags which are associated with these two. So when we say cross off, in the sense like if it is 2, prime is 2, then we are going to cross off in the sense make the flag of 2 to false, then 4 to false, then 6 to false, all in multiples of 2, right? And so once that is done, we come and find out what is the next prime. So the next prime in this case will be 3, right? But if we have a very large table, it won't be so consecutive numbers. There will be a lot of gaps in the numbers, right? And then we find a max, the next prime, and then again we go in this while loop, and at the end we return this flags table. Okay, so we can actually find out what are the least of prime numbers till for this particular number, right? So I'll just go quickly go through what is this cross off. It's very simple. It goes through, it takes this flag table and the prime number whatever you have just passed on to it, and goes through this for loop. And every time we look for a prime number, okay, and then we keep on finding it, and then we set it to false, and then we just move one prime to, like if it is 2, then we move to 4, therefore we just have to add the prime over and over again, right? 4 to 6, then 8, and so on and so forth, right? And for the next prime, it's nothing, very simple, just go through the whole flags table till it's not lesser than its size, and then find if it's not, if any of the flags is true. So whatever the flag is true, we return that as the next one. And if it is false, we just keep on moving ahead. That's very simple, right, to follow also. So this good part of the table, this function, as it will return all the list of any number. Okay, so I'll print some of them. In this case, I'm selecting a big number like 289, and if you see, it will return all these numbers over here, which are primes, right? So this is a very useful one. And in the way you were asking, Leon, like if we can actually use the same number here also, and then we just print out and we'll see, okay, these are the numbers which are supposed to have some values at least, correct? But in the case, if there is something, a number which is missing, that will be raised to 0 in this case, correct?
Mm.
So this was a very good way, because I think sometimes we might be asked about the way how to find a prime number, right? So I thought
Yeah.
that might be useful way of doing it, right?
How is that runtime complexity on the arrow? This
Well,
something is better than the square root.
We are storing the value.
so here it is actually the square root one only, right?
So the same runtime
Uh,
complexity as square root.
yeah, it should be actually, yeah.
Then why don't we use a square root?
We store the values also here, right?
Yeah, we store the values also, that's true. But he was talking about the time complexity. Yeah, so this is all a square root, right? So we can actually either say square root of max or use this way. Either of it works.
No, but is that really square root? Like because when we get the next prime, it's not like go one by one, right? It could like jump many places to go to the next prime.
Right.
So maybe less than the square root.
Yeah, maybe, yeah. Because you are saying like if it is 283, it's okay. In that case, it starts from 283. So it's jumping, yeah, almost like nothing. Yeah. Yeah, it might be, in fact, slightly, but that is the way we do, right? We have to find each and every prime number to that number. So we selected something like a 289. So we want to find all of them, right? Yeah, sorry, Shashank, what was that you wanted to add here?
No, I'm saying that we have already a table which keeps, which memorizes or what you say, the already computed value which you can use. I think in Wikipedia we have.
Yeah, but like if we go to the square root one, we also can print out one by one, right? I mean, like it had to be better than the square root one because this one use extra memory.
Yeah, if you see for the square root part, because we only deal with a single number for a square root, right? So when we start from 2, so if 289 square root, whatever it is, we go from 2 to that, right? So then from 3 again to square root of 289.
Oh, okay, yeah. Go
So
only
yeah, we have to going through each other. So it's slightly more time intense, but if you want to find all the least, then I think this is a good way of doing it. At least this is one of the way of doing it. There might be much better ways also of doing it, but I think this is also not that bad, right? As per the time complexity. Shashank, what do you say?
Yeah, I think it's, not that bad. It's equivalent to same only like previously. The root square root one, right?
Mhm.
Almost.
Yeah, because I've seen this being used many times and it keeps coming.
The elite code also we have.
Right. But I'm not sure if we can have something much better when we have to find a list of prime numbers. Okay, yeah, maybe, yeah, okay. So let me move on to one of the next topic, and I think these are the very simple ones. So now it talks about the probability. Okay, now the probability it can be it says that it can be a very complex topic, but let's go through some of the basic what rules or whatever you can say, laws, whatever of it. Like if the probability, if you want to find a probability of A and B, okay, in this case, probability of A and B will be A and B, and including this one, the intersection, right?
Yeah.
A and B, I think it should be only, okay, the intersection part, right?
yeah.
Yeah,
It's
it should
a
be only the
formula
intersection part.
like this.
Yeah. So what it says is like if you are given a probability of A and you know what is the percentage of B present in A, and if you just multiply both of them, so you'll get the intersection part of AB,
Yeah. So
right?
I think it's like this formula only. B, you have to find B. A is given. So this is equivalent to P of B intersection A upon the, A is given to us upon P of A into P of A. Right.
P of divided by P of A,
This is like
P of
probability
B,
of B given A. This one.
P
P
by,
B.
oh, PB by, okay. Uh-huh.
Yeah, yeah. And that is equal to this B intersection A upon P of A into P of A. So if you take intersection this part, then P of A will go there, right?
Hmm. Okay, interesting. Yeah.
This From there only this relation is there. Right?
Okay. So if you want
If
to
you want
divide two of them, so this is the way we
this
do
is
it,
the
right?
intersection. Yeah.
Interesting. Okay, yeah, that's very good. Thank you. Thanks for
Yeah.
sharing it. Yeah. So then actually there is one example what is stated in the book. It says like if we have given a numbers from 1 to 10 inclusive, okay, and if you want to find a probability of picking an even number and a number between 1 and 5, if you want to do it that way. So he says that if you want to find a probability of finding a number between 1 and 5 will be 50% of what it was for 1 and 10, right? So the probability will be 1/2, correct?
Yeah.
And if you want to find an even number, okay, so that boils down to one of five, it will be 40%, like 2/5, because we have just two numbers even in one and five, right? So
One
therefore,
minus that also we can do complement.
yeah, we can do a complement of it, right? Yeah. So therefore, if we actually find both of them, it's going to be 1/5. So if the probability of x is even and it is less than or equal to 5, it is going to be 2/5 multiplied by 1/2, which is equal to 1/5. Right? Yeah.
What the probability of B given A? What does it mean?
It
It
means,
means
yeah, go ahead.
like you thrown a dice, right? Now you have to A has already happened. Now you have to find what is the probability of happening of B.
Yeah, what is the portion of B which is in A?
Yeah.
Yeah, so that is what
Yeah.
it says. Yeah.
Okay.
Yeah. So then if you go for probability of A or B, right? So it will be probability of A plus probability of B minus the intersection of A and B, because you're counting it twice, right? In this case.
Yeah.
Yeah. So we just have to subtract this part. So in this case, he says you calculate this one first, right? And then you just add both of these probabilities and subtract this one, the top one, right?
Mm.
Yeah.
So in case that A and B there's no overlap, then the intersection will be
Zero.
zero.
Yeah.
Right?
Yeah, but that is what independence means, right? If they are not
Mutual.
actually overlapping. So it will be
That
PA into PB. So he says that if A and B are independent,
Mm.
and if one happening tells you nothing about other happening, okay, so then it will be PA into PB. If there is no dependency, and if there is mutual exclusivity also. So what does that mean is if one happens, then the other cannot happen. Okay, at a time if only A is to happen, then B is not going to happen. If B happens, A is not going to happen, then the probability of that in that case is going to be PA plus PB. Yeah. So I think, yeah, these are some of the things what talked about. And then yeah, some of the things what is saying, sometimes you still will be asked some of the brain teaser question to start with. So don't panic, and then you try to handle it methodically. So that is what the interviewer expects. He also knows that you are not going to solve it, or he doesn't expect any answer from you, but the way you start approaching the problem is very important. So it's like very small steps you take one by one and write down all the rules or the steps whatever you're going through, but be very what you say, like a sort of, the approach should be very methodical, and it should be more organized, right? So that is what they like about those things. Even if we are not able to find anything at the end of the interview, that's still fine, but the approach is more important. That is what they are trying to judge us upon, or else we keep on just throwing some sentences here and there. That doesn't make sense, right? So for that, actually, they're giving a small example. Okay, it says like if you are given two ropes, okay, and each rope is of uneven densities, and if we burn one rope at a time, it will take 1 hour. So both ropes are like that; they can actually burn for an hour. So if both one starts burning, it will burn for 1 hour, and the second one, if you start off with that, and we start burning that again, it actually again goes for an hour. And in that case, if you want to find a time exactly of 15 minutes, how do you work on that? Okay, so I think this is also a famous problem, right? So yeah.
And how is that? How is the rope burning problem? Is that related to the probability? Or
No. Actually, he's talking about, because this whole chapter is about math and puzzles, right? Brain teasers and everything. So I'm just picking up whatever is relevant for the maths and the logic problems. But in some cases, these are very famous problems which some of the people still ask as a, whenever you start with an interview, sometimes to just an ice breaking questions, right? So they just start with some of these questions. And in some cases, they are very easy. So if you don't even know about it, it's always good to know about them, right? But then in that case, we still have to go through the flow. So it just says don't get panic, and how do we approach them. So the best thing is just the approach is more important. The way you think, even if it's wrong, it's still fine, but the method, what you are trying to do, right? So in this case, when he says about this two approach, what he says, you write down all the rules. And the first rule, what he says, okay, you can say a rope which takes x minutes to burn, okay, and the another takes y minutes to burn. And then if you have both of them together, one after another, it will be x plus y minutes, right? That's the simple thing. And then, so even it says that the rope, even if you light it from the middle, it's not going to matter, okay? Because it's not, if you just light it from, because the densities are different. So even if you light in middle, because you never know how much time you're going to get, so that won't matter. So just keep on discussing all of those things. But if the rope actually is lighted at both the ends, okay, it will finish in 30 minutes. So that is the first rule you can write about. Then you can say, when you do that, uh, so if you are done with 30, so we should be able to do within 15. So what we will be thinking, like think loud about all those things. So we can actually do with, for the first row we can take, okay, and then we light the both ends of the first rope, okay, and take the second rope also and only light one of the end of the rope. So when the first rope finishes within 30 minutes, okay, at that time the second rope will also finish 30 minutes, half of it. At that time you actually start the other side of the second rope, so you can find 15 minutes, right? So if you find that formula like y minus x by 2, right? So that actually will give you the 15 minutes duration, how you might come to that. So the approach will be like, you can write light rope 1 from both ends, and rope 2 only on one end. And then when both, in the second step will be with both of them flames of rope 1 meet, that will be 30 minutes have passed, and then you start light the other side of the rope 2, which will take to 15 minutes, right? So those actually steps, if we can, very well explain it, or show that that is a way approach we would like to go through that. So that's a really good way of doing it. Okay. So then there is one more question about worst case shifting, and in some cases how we can do that, and that's one more a puzzle sort of question. It says that if we are given 9 balls, and it's very famous interview question again, and 8 balls are of the same weight, and only one ball is heavier, okay, and then you are given a balance, okay. So the balance actually only says which side is heavy, the left side is heavy or the right side is heavy. That's the only thing you can say. Or if it's not heavy, it's the same, it's not going to show you, it will be equal, right? So in that case, if you are allowed to use the balance only twice, so how are you going to solve this problem? So that is
So
what he talks about, the minimizing an action. Yeah, go ahead, Shashank.
I'm telling you take 3 balls on one pan and other 3 ball on other pan. If both the pans are equal in weight, that means all the 6 are similar, right? Now you are left with 2 balls. Now you put both one on one, other on other pan. If any one of them imbalances, that means you got that ball. This is one case, right?
Perfect. Yeah. Yeah,
And
that's the correct one actually. You said it.
yeah.
So if we had 9 balls, right? So out of that, you know that 8 balls are of the same size, and only the ninth ball is heavy. So you are saying that you group them into three and
Yeah.
take two groups together and do a weight of those two, and both of them are same. Then they just throw it away and take the last group of three, and then you split them in one. Okay, put that in the way the way
Yeah.
weighing machine, and if both of them are actually same, in that case just throw them, and the last one which is remaining will be the heavier ball, or else you will find whichever is heavier on the weighing
And
scale itself, right? Yeah, absolutely, yeah. So but initially, I also was tripped off when you say, oh, 9 balls, and how do we do it? Like, I thought of taking 4 because you always try, used to take, you are used so much to take the maximum possible and try to eliminate, but that doesn't work in this case, right? So if you take
yeah,
4, then it's very difficult.
more number of pans you will have to use. I mean, more
Right.
number of.
Yeah. So that will actually increase your worst case balancing. So how do we minimize it? In that case, the later decision, what you said, we have taken maximum size. Why don't we reduce it in three? And that's a very smart way of doing it. Absolutely. Right. Yeah. So these are some of the things what discussed in the book, and they are really good. So now we'll just go through some of the problems. I think these are some of the ones which are very easy also. So one is about the heavy pill. Okay. So if you read this, okay, just let me. Okay. So the heavy pill says that you have uh, 20 bottles. Okay, 20 bottles of pills. 19 bottles have 1 gram pills. Okay, and only one has pills of 1.1 gram, right? And then you are given a scale that provides an exact measurement. How would you find the heavy bottle? And you can use the scale only once, right? So it is like we have 20 bottle of pills, and each bottle in the of this will have a weight. So 19 bottles have pills of one. Each pill in the all the 19 bottles are of 1 gram, and each pill in the last bottle, okay, is of 1.1. So we want to find which is the heavier bottle. Yeah. So you could actually, I think Shashank should be able to get a
Yeah,
clue on this, right? Yeah.
same way, like, isn't it? It should go 9 9 if you take what you said. Here, maximum should work, right?
Right. So, okay, this is slightly different, but what it says, and actually, it's not very clearly stated. Therefore, actually, it's sometimes become more difficult to understand and actually analyze it. So, what it says, each bottle will have many pills. Okay, so that will be
Mm.
standard pills. So, and a bottle will have many pills. So, each pill is about 1 gram, and in the heavier bottle it is 1.1 gram, right? So there will be many pills in each bottle. So that is the first thing, if we get a clue of it. And then what he says, in this case, what you can do is, now you are allowed to take the scale of only once, right? So you number the bottles from 1 to 20, and from the first bottle you pick only one pill, right? From the second bottle you pick two pills. Okay. Oh man, what happened? Why went that? Okay, I don't know why it's down. Okay. Second bottle, you only two pills. And the third, I did something.
Annotator you can use directly.
Yeah. What happened? Okay. Second bottle, two pills. Okay. So if I just annotate in that case, sorry about that. Okay. So, okay. So the first bottle, you can take one pill. Second bottle, you can take two pills. Third bottle, you take three. 4, and so on and so forth till your 20th bottle. Okay. And now when you weigh them, so what are you supposed to get? If they are all of 111 gram, so you will get some weight as like 210.
N into n plus 1, yeah.
Yeah, so it's like 20 into 21 by
10,
2,
2.
right? Yeah.
Yeah.
So you get this. But in this case, you know that there is one bottle which has 0.1 gram extra. Correct. So in this case, if we get weight, okay, something like 211.3, okay. So what you can do is this way, 211.3 subtract from 210, so you'll get 1.3, and then you divide by this zero point 0.1 grams. So you'll get 13. So you can very well say that your 13th bottle is the one which is heavy.
So 2.113, it's like you added 1.1.
Yeah. So it says like the weight what you get minus 210 grams, okay, and then you know that this will be the difference, right? So if you just divide this by zero point 0.1 grams, okay, so that will be the bottle number, right? Because so each and every bottle, like if this is bottle one, it has pills of 1 gram, so this will be 1 gram, this will be 2 grams, 1 plus 2 will be 3, and 3 will be 6, and so on. When you come to 13, right? So in this case, 13 will be 13 point, what it will be like 1 into 1, 1.1. So it will be 3 and 1, 3 and 1. So it will be 14.3, right? So you'll actually, instead of adding 13, you'll be adding 1.3 more, right? So this 1.3 actually is what we will be getting here if we subtract weights minus the total number of weight which we are supposed to get for if they were all of 1 grams, right? And then you divide by the weight for each pill because you got an extra of 1.3. So if you divide that by 0.1, you're going to get the number of the bottle number. Yeah, I think this is a very good way, to get some of these problems. Yeah, but it's not a very quick way of coming. But I think, yeah.
Yeah, the difference of weights you are calculating and dividing it by the interval.
Correct. Yeah.
So, like, but how you get 211.3? Like 1.1 into 20 you did, right? Or directly to 210.
2111.3. Okay. What you are saying? Okay, he
Two.
says, okay, so at least you got this, right? If you are 1 to, okay, then if till 20, and if they were all of 1 grams, right? So you will get 210. This is the ideal case. In case if we don't have a bottle which is of 1.1 grams. This is clear, no?
Yeah, this is clear.
Yeah. So he's saying that in this, when you actually take pills like this, okay, and then if you get something like 2111.3, so
Yeah.
why we are getting 1.3 extra is because the 13th bottle is of size of pills 1.1 grams, right?
Yeah.
So 13 multiplied by 1.1 will give you something like 14.3.
143. Yeah,
Yeah,
14.3.
14.3. So that it was expected to be 13, but it is giving us 14.3. And if you check the difference, it is 1.3, right?
Yeah.
Because we are actually taking zero point 0.1 grams of 13 pills. We are adding that. So
Yeah.
it is a simple math actually problem, but if
Yeah.
it was a 10, then it would be something like
One.
1.1.
Actually.
Yeah, right. Yeah.
Because each
One,
pill,
sorry, yeah.
yeah, each pill is 0.1 extra, right?
Right.
So you have you at bottle number 10. That means you had 10 pills in there.
Right.
Right? So 0.1 times 10 is 1.
One, yeah.
One.
Right, right.
Yeah.
Exactly. So it will be 211 in that case, right? So we can easily find what is the number of bottle. So I like this puzzle. It is very simple also, right? And
Yeah.
now this is about another problem, which is our very famous problem about egg dropping problem. Okay. I think we all know about it, right? Yeah, it is a sort of a DP,
Yeah.
right? So, well, okay. So he says that there is a building of 100 floors, okay, and okay, let me see if I have. uh, you can see my screen, right?
Yeah.
Oh, oh yeah. So am I not sharing the OneNote till now?
Yeah, OneNote is there.
You don't see my lead code?
No
No.
lead code I'm not seeing.
Okay, sorry. Let me share that. Okay, so okay, you see the lead code one, right?
Yeah.
Okay. So now, okay, sorry. Let me go back again. In this case, if we go to, let's read the problem. He says that there is a building of 100 floors, and if an egg drops, okay, from the nth floor or above, it will break. If it is dropped from any floor below, it won't break. You are given two eggs. Find n while minimizing the number of drops for the worst case. Okay. So what are the approaches? I think this is a DP problem many one of us has gone through, right? I understand it's not a straightforward one. So okay, I'll start going through this. You guys also help me, you know. So what he says, what is said in the book, okay, and I think we should always say what she says. Okay,
Yeah.
so yeah, that's the problem, you know. Sorry about it. Yeah, so it says like if we have two eggs and if we do a linear search from the lowest to the highest between breaking floors and all those things, if you want to find a breaking floor, right? So we take an egg one, okay. If we have just one egg, so and we have to find out what is the floor which it will break, right? So for that I have to go to each and every floor and drop it, right? We start from the first floor, keep on doing till the 100th floor. And wherever it blocks, I will say that is my floor which I will say is a breaking floor, right? So if it is breaking, so the floors above that will all be breaking, and till I don't hit a breaking floor, I keep going that if I have an egg one. But if I have an egg two, then I can have more chances, right? So in that case, what it says is if you can start with the floor, something like a 10th floor, okay, then you move to 10 plus, sorry, then you go to 20, then you go to 30 and all that stuff, right? And then whenever you find a floor which is breaking, like if you come to like 40th floor, if it is breaking, so then you can come back to between the gaps between 30 and 40, and then you can do 1 1 1, like you can start with 31 32 33 34 35 linearly till the 30, no, 40 39th floor, from 31 to 39 with your second egg, and then you can find it, right? So in this case, the disadvantage is because it depends on all on the floors and how much times you are going to attempt, right? So if the breaking floor was something, it says like a 99, in that case you will take 19 drops, right? So you'll start with 10 20 till 90, that will be 9, and then you will start from 91 to 99, okay, that will be another 10, so it will be 19 drops, right? But if it was something like 40 second, okay, so what you would do is like 5 drops for 10 20 30 40 50, and then 41 42, like it will be just 2 drops more, right? So it will be 6, or maybe a maximum something like 4 plus 9 13. So he says that the moves or the tries what we are doing, it's not uniform, so we have to do some sort of load balancing, and we should actually see that whenever we try to drop these eggs 1 and 2, they should have a uniform tries, or the moves, right? So it should not be a big difference, right? So in that case, the one what is suggested in this book, the approach is like you start from any number, right? Maybe some ad hoc number, if it is something like an X floor, okay, and then every time you do that, okay, so if you start with some X floor, So next time when you do, you actually do with x minus 1. Okay, then you do x minus 2, then you do x minus 3, and so on and so forth, right, till you reach the end. Okay, so if we do it that way, correct, until we go to the end, and if we add all of these, right, so because if we keep on adding, so at that end we will come to 1. So we know what this formula will represent, right? So it will be something like x into x plus 1, okay, divided by 2. And if our floors are 100, so we can find what will be our drop, what we start with, right? So if we can start that, in this case, it is something, it's a decimal value, float value, it is 13.65. So now we have two ways to take this value. One will be 13 or other will be 14, right? So if we take 13, so the maximum floors what we can go will be 91 only. But if we take 14, you can actually go to 105 floors. So therefore, they select usually the 14, which is the most optimum one. Right. So whenever we select 14 and then we try to find any breaking point, okay, so the maximum tries will be 14 or below 14. It's not going to be like 19 or more, even if the floors increase, so we'll always have this maximum. It will limit to 14. So that is what actually this problem talks about in this book, but the way we are actually used to in the lead code is a slightly different way. We try to find the floor, right? If I'm not mistaken. Okay, maybe I'll just go to this guy. Okay, so what is shown in this, we find a breaking point. So in this case, this is the breaking point, and then we have to count the number of drops. Okay, so this is the breaking point function, what it said you pass on the floors, and the breaking point now I'm setting to 68, and I'm giving an interval of 14. Okay, so if I give an interval of 14, so let us see if we can get, if we get the breaking point, we can get a breaking point 68. That's true, it we will surely get, but then the drops required are 14 in that case. Okay, and then if we actually change this breaking point to some other value, maybe like 65, okay, so it will surely reduce, right, in that case. So it's going to take 11, right, but it's not going to go more than 14, right? So even if we take 71 or 72, it will reduce to 10, right? So because 14 was the maximum, so it keeps on going from lower point 14 and then go down and up based on what the interval is we are selecting for the breaking point, right? So that is what is said in the book. It says, like, if you go through this, it's a very simple way of drawing. You take the first egg, you keep dropping it from the selected floors. Okay, so this is the egg 1. You start with interval, which is 14. Okay, and then you keep on decrementing your interval 1 at a time. And then whenever you cross your the floors, so it means that you have to stop the egg 1. Okay, then you have to start with the second egg, and the second egg actually you are incrementing by single ones, not by the leftover intervals, right? So one by one you have to go, because you start from the previous floor, because breaking floor would be in this case previous floor plus 1. Then you have to go from the previous floor, start from the previous floor plus 1. Okay, and then you keep on going through each and every egg, the second egg, one at a time, and then find what is the exact floor, breaking floor. So this was the whole what you say about the problem in the book. But if we actually look for the super egg problem, I'll just go through the one what we have. I'm sorry. Okay, just I'll open that in. So super egg problem, right? super egg drop. Sorry, yeah. We'll just quickly go through that. So actually, it will make sense because most of the time I also have a lot of difficulties in following because it was slightly different in the book what is represented, and in this case, if you look at the lead code one, right? So he talks about this is a super egg drop problem, which is a hard problem, and it says that you are given k eggs. Okay, it's more generic problem over here, and then you have an access to a building with n floors from 1 to n. Okay, if each egg is identical in function, and if an egg breaks, you cannot drop it again. Okay, that's clear. And then if you know that there is a floor f which is from 0 to n, such that any egg dropped at a floor higher than f will break. So it means this is a breaking point f, right? And any egg dropped at or below f will not break. Okay, so each move you may take an egg, okay, if you have an unbroken one, and drop it from any floor, okay, x. So it will be x will be between 1 to n. So your goal is to know with certainty what the value of f is, right? So here we're trying to find the breaking floor, right? And so what is the maximum numbers of moves that you need to know with certainty what f is regardless of the initial value of f? Okay, so so if you are given an example here like k is equal to 1 and n is 2, so in this case we know, right? So if we have a single egg, it will always be the number of floors, as simple as that, right? Because we don't have any other way. And also we'll use that many number of tries because we'll have to go to each and every floor and drop it and see. So if it was 100 floors, k is equal to 1, so we'll still go one by one. And if it breaks on 100 floor, you will have to go to the 100 floor, right? So that will be 100 moves, 100 tries, and your output also will be whatever that n will be. Correct? Yeah, and then in this case, if you have 2, so this will be 6. Okay. So in this case, we can use the same way what we were discussing, like if we start with 14, 13, like that. But here, if we can't start with 14 because n is lesser than 14, right? So what is the best way to do? So if you have 2 eggs, and how we can do it in 3 moves only? Or, oh yeah, this is the floor what we are finding, right?
Number of floors.
Yeah. So if we have the first egg, we can actually start with something like 1, 2, 3, right? If we are like that, then we can drop from that floor, third floor. And if we are able to find, then that won't matter, right? Oh yeah. So in this case, it will be something like this. Okay. So if we have this floors, right? So 6, 5, 4, 3, 2, and 1. And then if we have 2 eggs, so what is the best way to do? We can actually start from this floor. We drop it, right? So if we drop it and if it breaks, we have still one more egg, and then we can use this floor with that second egg. Then if it doesn't break, it means this is the floor. Okay. But in this case, if for the 2 it doesn't break, okay, then you can still go on this floor, okay, with the egg 2, right? So if egg 1 doesn't break here, so you can still go to the egg third floor and you try a drop. So that is what the 3 will be in this case, right? Well, it's slightly, it is always not so clear about these things in the problem, right? At least I'm not very clear about why it is like that, but yeah. So it says like you have k is equal to 2 and n is equal to 6, and if you say your 3 is the breaking point, okay, or is it like that you can find maximum of 3 floors in this case, and that is for sure, right? Okay.
Yeah.
because at least you can have 3 floors with the 2 eggs. You can surely say that I can reach 3 floors. Okay, because if you start with, say, okay, I'll start from the 3rd floor, and if your egg breaks, okay, then if you start going from 1 2, so that won't be the minimum number of moves, right? Because then you will start from 1 and 2, it will be 3. Okay, then for the 4th one it will be 4. So he's trying to find the minimum moves also, maybe, or maybe the max for certainty. Yeah, he talks about with the certainty how much you can have for
I
this
think
floor.
max only.
Yeah, so we are sure that these many floors we can surely identify. That is what he talks about. Yeah, okay, that makes sense. But in this case, it's a DP problem, right? So you can solve it with um, the top-down approach or the bottom-up approach, right? So I have all these solutions here, and they are also like we might have solved in one of the lead code sessions. So I'll just go through them very quickly. I don't want to spend more time on this, right? So the first problem here, the first way to solve with the top-down approach was very simple, right? You have a memo here, and then I'm using this helper function with k is the number of eggs and n is the number of floors, and this is my memo, and the memo is 2D. One is for the k plus 1 eggs, and one is for the number of floors, right? So if we look at this helper function, so this helper function actually, when your n is 0 or n is equal to 1, it means you just return n, that's true. And if your k is equal to 1, it means you have only single egg, so you return whatever your n was, right? So in this case, then you start from the first floor to n, and then you use two helper functions, right? So the first helper function here, in this case, when it says k minus 1, it means that we found one floor which breaks. Therefore, we are reducing one egg. So if it doesn't break, it means we take that egg again. But in that case, we are reducing the number of floors. So x is the floor, so which we are on, right? So whenever we keep on going from 1 to n, and at each and every floor, so we know that if at a particular x, your egg is not breaking, so you are left with n minus x floor. And so therefore you have to explore only n minus x floors, right? And in this case, you know that you have already dropped an egg, so which has broken. So you have only one, you have an egg less in this case, k minus 1, therefore. And also you have to check for floors below x minus 1. So that is what, and then whatever the value you get from these two functions, whatever the maximum value you get, okay, you add that one with 1 because that is the current floor what you are on. Okay, and then you do this for each and every floor from 1 to n, and that minimum value, whatever is the most minimum value, so the maximization of the minimum value, okay, or the minimization of the maximum value, so that value will be a real value, correct? So yeah, so in this, the top down approach, even if you use memoization, it TLEs on some of the test cases. Okay, so as per the lead code, we should find a much better way of doing it. And then the reason what it goes to is like you can use a binary search, right? So this is also bottom up approach. It is almost the same as what is being done, but this also TLEs. Okay, it's exactly the same way. Okay, but it's a bottom up approach. So this also TLEs, but then for that, the way it should really be done. I think Roger also has gone through this solution, right? So you use a sort of a binary search. Okay, it is also not that difficult. All of these things remain the same, what we saw, but then we use a left and right, which starts from 1 to n, okay? And then we divide this L by n in a midpoint, okay? And then you take this midpoint here, so mid minus 1. So you assume instead of going from 1 to n linearly, okay? So you keep on jumping the binary search way, okay? So in this case, I will find a term 1 value, whatever it will be for, I'm assuming that my egg breaks on this one. So I will also reduce my current floor, which is the mid value. And in this case, my egg is not breaking, and then what will be my n minus mid? So if when I have this T1, T2, okay, then I just find the minimum of them with the maximum same minimum of the maximization, some that formula, right? So the same thing, I keep on storing it, but in the same way, at the same time, I go through this binary search and then find if my T1, T2 are equal, then only I break. If it is not, then I try to reduce my search space of binary search, right? So if it is T1 is less than T2, okay, I know that my search space is slightly very wide, so I have to reduce it, and then I actually set my the left side to mid plus one or my right side to mid, and then I narrow down my search space till I don't get to this T1 equals T2, right? And then whatever is the value I get, and I just store, and then this one actually works. Okay, so this was, and actually this is the only problem or the solution which passes, okay, in the lead code at least.
So it's log n then, right?
Yeah, it is n log n. Yeah,
For intention.
yeah. So then actually there is another problem which the way it is solved, and it says, yeah, you can actually use this function. I think Roger explained this one also, I think. So you just use the same binary search value, find the mid value, but then use this function. And this function is slightly very different in the sense this is like represent eggs. So you go from your first egg to the number of eggs, max eggs, and every time you are going to that, you actually store that value. So this value will be something like, so your x, your whatever that x is a floor value, because this will be your mid value. So for the first egg, it will be x value which will be storing, but for the, if we have a second egg, it will be x minus 1 divided by 2. Okay, and so if we had another egg, it would be x minus 2 divided by 3, so on and so forth. So it's like this will be something like the factorial of 1 2 3. Yeah, so maybe this is r factorial, something like combinatory, something like that, right? And this is x into x minus 1 till you keep on reducing. So this is a very smart way of doing it. Okay, and whenever we exceed the number of floors, you break. Okay, and then for that, so whenever you are passing any value of the mid value in here, you can quickly get, okay, what is the maximum floors you can reach based on the tries. Okay, so based on that, you can actually adjust your binary search very quickly, right? So in this case, you can just go, okay, just pass in the mid value and find out how many floors for this particular mid you can go. Okay, and then you keep on changing your this mid value, so you can converge on your range very quickly. Okay, while in this case it was slightly more because you keep on doing it for long. Okay, and then you see if they both are same. You are trying to depend on these two recursive functions, correct? So but in this case you don't do that, right? So you are just depending only on the floor and this the eggs, number of eggs, and that's a simple formula what you have to go through, right? So you're not running through each and every floor, and that is the reason actually this is more efficient, but it's very difficult to come up with this solution. But just wanted to highlight here, and most of the people and most of the discussions are also talking about this solution, and it's a very good way of doing it. Okay, so this was one. Okay, so there are some of one more problem, I think, about the lockers in the hallway. Okay, I think we are almost closer to time. I'll just quickly go through this. And this is about a 100 locker problem. I think this we have also done in one of our lead code session. It talks about that there are suppose like 100 closed lockers in a hallway, and a man begins by opening all the 100 lockers. Okay, and next he closes every second locker. right? So then on the third pass, he toggles every third locker. And for the first and the fourth, he will actually do again do it for the fourth pass till he reaches, like for each and every pass, he will do a toggle for each and every locker. So after the 100th pass in the hallway, he will toggle only the 100th locker. So at the end of whatever he has done, okay, the toggling from one pass to 100 pass, so how many lockers will remain open? I think this is a very classic problem that we have also gone through, right?
Yeah.
So if we had some lockers like this 1, 2, 3, 4, 5, okay, 3, 4, 4, 5, 6, 7, 8, 9, and 10. I just take 10, right, in this case. And so if we start doing it, initially they are all closed, and then he opens them. Yeah. So now initially they are all open. Then he goes for the first locker. So the first locker is open. Then he goes to the for the second pass. In that case, second pass actually will be closed, right? Then he goes for second. Then he goes for fourth. Also, fourth also will be zero in that case, right? So if he keeps on doing this, okay, for 1, 4, 5, something like that, okay. So at the end, what happens, I'll just go through, jump to the conclusion here, is like for the fourth it will be 1, okay, in this case. Fifth will be 0, sixth will be 0, seventh will be 0, eighth will be 0, ninth will be 1, and 10th also will be 0. So what it says, so the lockers at numbers which are perfect squares, okay, those only lockers will be open, rest all will be closed. And the reason is because if we take any number, okay, if we take something like 6, so the 6 number actually can be a product of 1, okay, into 6, right, and also 2 into 3, right? So it can, if you see, it is actually 1 pass, 2 pass, 3 pass, and 4 pass. So after 4 pass, it will be, because it is even number of pass, so therefore it will be closed. But if you go for like a 9, okay, in that case what will happen? So we have 1 pass, 1 into 9, right, and the second will be 3 into 3. So if you see, we have only odd number of passes, right? So 1 for 1 pass, 9 for 9 pass, but for both threes it will be only 1 pass. So therefore this will be odd number of passes, and therefore this locker will remain always open. So whenever we have perfect squares, right, so those lockers will always be open. So that is what the whole solution boils down to.
For bulb switch, it's like
Right.
good.
Yeah, we have that bulb switching, correct.
Yeah.
Yeah. So this was these were the only problems which I came up with. Okay. So there is one more problem I thought, but it's okay. So this is the last one I would, and then I would like to know about you guys. Anyone has any questions to? Oh, I think so. I'm sorry about all this. Yeah, you followed about. Thank you, Shashank.
Yeah.
Yeah, you followed the chat. Yeah. So this was actually what I was discussing, and I actually got and was prepared to discuss more on this chapter. Okay, so with this, I will stop the recording if you guys don't have any questions. Okay.